Okay, welcome back. We will continue now with lecture 4. So we talked 3 lectures. We talked about signals, signal properties, multiple access, how the signal is generated or multiplexed onto one carrier frequency. And now we will move to the receiver the first time. So we will talk today about signal acquisition. Then tomorrow in the morning, we'll talk a little bit about propagation effects. So what is happening in between transmitter and receiver. And on the 6th lecture tomorrow afternoon, we will then finally go into parameter tracking, which is estimation of time delay, phase, and Doppler frequency. So today we will introduce the first, let's say, part of the signal processing in a GNSS receiver, which is acquisition. I will talk a little bit about acquisition and how it's related to the other parts in the introduction. Then we talk about Doppler and time estimation, so joint Doppler and time estimation, which is vital for acquisition. Then about a detection problem, because we need to detect and we need to estimate. So it's a joint estimation and detection problem that we will tackle with acquisition. So we will estimate coarsely Doppler and time delay and detect whether a signal of a satellite is present or not. Because when we start navigating, or we don't know which satellites we receive. And in the end, we will look at a basic methodology how to implement or how to perform parallel time delay acquisition. We only look at one method here as an example. There's many different approaches how this can be done. So in general, we have this is an overview of the complete signal processing of a GNSS receiver. We can also highlight with this again the 2 parts of our course. The first 6 lectures are about this part here on the left, so about acquisition, tracking, and the signals. And the rest of the course, starting from Thursday till Tuesday next week, it will deal with the navigation processing. So the first part is providing estimates of Doppler, delay, and phase. And in the second part of the course, my colleagues from UPC, they will tell you what needs to be done to use these estimates to end up with an estimate of the position. Yeah, and you can see here in the signal processing, we have 2 main parts, acquisition and tracking. Acquisition is somehow an initialization of the synchronization process. Then acquisition hands over some initial estimates to the tracking. The tracking is refining these parameters, estimates, and is following the change of the parameters over time, when the channel changes over time. And if the tracking is lost, this can happen, then we have to usually go back to acquisition and restart the tracking again. Yeah, so signal acquisition provides a rough estimate of the signal Doppler shift and time delay. This is important to perform correlation. We not only have to estimate the time delay, but also the Doppler shift. If, for example, a Doppler shift is quite large and we make a large estimation error, it can happen that we maybe cannot, the processing gain is not enough to really have a meaningful signal after or estimate of the time delay. We have to solve a maximum likelihood estimation problem in a coarse resolution. Usually the acquisition does not need to be so exact to initialize then the tracking. We have also to detect the received satellites, so which are separated by codes in the DC ds-CDMA. And for each satellite, correlator outputs with the same time delay and Doppler shift from different epochs periods are used to form a decision variable. If this decision variable passes a threshold, the signal from a certain satellite is assumed to be present and received. So this is the detection problem. We will detect whether we receive this decision variable is above a certain threshold, and then we will say that the satellite is received with the parameter estimates time delay on Doppler, or not when this decision variable is below this threshold. Time delay and Doppler shift estimates are used to initialize then afterwards the tracking loops. Yeah, how can we jointly estimate Doppler and time delay? I mean, we already worked on the maximum likelihood estimator for time delay estimation, and now we will see that when we start with a signal model that didn't include Doppler shift, right? So it didn't include Doppler shift, it didn't include phase at all. It was a fully real numbered signal model. Now we move to a signal model that is complex valued. So the noise is then also complex, which is given here in n. So we return to our vector-based signal model, and now we have, instead of all the other parameters that we already knew from before, like the power, we have now also a phase, a carrier phase. We have the navigation message. Still have our code sequence delayed by tau. And this is now here the Hadamard-Schur product is the element by element wise multiplication. And we have then here the estimated Doppler shift also included in a vector, and this new vector D here is the sampled Doppler frequency shift. As we can see, this goes from KN-TS to KN plus N minus 1 TS in the case observation interval or period. Again, we assume, n runs from 0 to n minus 1, k runs from 0 to k minus 1. So capital K is the number of periods that we are going to consider, and then there is n samples usually per period, and nd is the number of chips. So we assume we have more samples than chips, maybe 2, 3 samples per chip. And we also have an integer number of samples per chip in this model. So, okay, the new stuff here is the Doppler frequency, which is a complex vector, and the phase, which is also a complex number here. All this other stuff, G of K is real, is minus 101. C is also real, delayed by tau. And P is also real, and also now the noise is complex, and before it was real. Yeah, so we assume that the signal is filtered with an ideal low-pass filter, as we had this also defined in our signal model before, and subsequently sampled with a sampling frequency of 1 over TS, and this is equivalent to 2B. And the low-pass filter has exactly the bandwidth of B, the one-sided bandwidth of B. Thus, the noise after this filtering and sampling is still complex white Gaussian noise, even though it was filtered, but due to the sampling at exactly the rate of 2B, the sampled version of the noise is uncorrelated in time, and that's why we can still consider complex white Gaussian noise here. So the expectation of the noise vector is a 0 vector. The expectation of the L2 norm square of the noise is n times sigma n squared. That's the same as assumed before, and we also assumed this before already, that nk of n Hermitian, which is conjugate transpose, the expectation of this is sigma n squared times the identity matrix of dimension n. We assume that the quantization noise, which means the how many steps of quantization we use and so on, in the receiver, and thermal noise from the antenna and the LNA are included in N, and thus the sigma N square is effectively 2bN0 plus 2 times the variance of the quantization noise. We can assume that the quantization noise is Gaussian distributed if we have a certain number of bits that we use for quantization. If we are, for example, with 6 to 8 bits, this is a very good assumption to assume complex Gaussian noise. For lower quantization, we have to be very careful about the noise statistics. Yeah, again, as for only considering the time delay, we will only consider one period. So we will define now that the vector x is x at the period 0. And we assume again that a random variable of a multivariate Gaussian probability density function. So x is a multivariate Gaussian probability density is a multivariate has a multivariate Gaussian probability density function, and this function is parameterized by the parameters theta, and this is tau in nu. So tau the time delay, nu the Doppler shift, phi the phase, p the power, and g of 0 the data. So these are all the things that are not known. And thus we can get this is this PDF that we have here now. We talked about this, about the likelihood and the PDF, but I can repeat that here. The likelihood function with respect to the parameter vector theta is given as L of x parameterized by theta, and this is equivalent to the probability density function of x, where x is a realization of the random variable x parameterized by theta. The likelihood is a function of the parameter vector theta, which is to be estimated at a given realization of the random variable x. And the PDF is a function of the realization of the random variable x for a fixed value of theta. So our case is we will use the likelihood because we are receiving a realization of the random variable x. This is the vector x is our signal that we receive at the period k. And we're trying to find now the parameter vector theta that parameterizes this received realization as possible. And how can we do that? First of all, we can say, okay, let's reparameterize the problem a little bit. Let's say that alpha is the square root of p times the exponential function of j phi times g of 0. And then the parameter vector theta, we can rewrite this as tau, nu, and alpha. So we have 3 unknown or 3 parameters now. While alpha is a complex parameter. Now the maximum likelihood estimator can be again given by that we maximize the likelihood with respect to theta, and from this we get the expectation, the estimate theta, and we can also, instead of maximizing likelihood, and maximize the log likelihood, or in our case we can use the natural logarithm. This facilitates a lot the formulation of the problem. Yeah, the MLE is asymptotically for large n unbiased and efficient. I explained that already before, but if unbiased means that the expectation of the estimates theta hat is 0, and that the expectation of the estimation error is 0, and yeah, and so theta hat minus theta is 0. This is unbiased, and efficient means that this estimator attains the Kramer-Hall lower bound for this problem. We could also calculate one of these bounds for this problem. Yeah, when further deriving now the estimator, we can apply the logarithm to the PDF, and we arrive here with the first equation here. So arc max of log 1 minus and so on. We can now forget about, or we can yeah, we can leave out or we can neglect the terms that are not dependent on theta, right? So the first one, the second one, we can further expand the third one. And we can also neglect this factor here, 1 over sigma n square, because it doesn't influence at all the result. And then when we expand here this L2 norm square, we get minus x Hermitian x plus alpha conjugate C of tau Hadamard d 0 of nu Hermitian x plus alpha x Hermitian times C tau Hadamard d0 nu. And then the last term is minus alpha conjugate alpha C Hadamard d Hermitian times C Hadamard d this right. So now we see that also several terms do not depend. The first term especially does not depend on theta. We can also remove that. And we get to the cost function j of theta, which is then just the remaining 3 terms. So now taking the derivative of j of theta with respect to alpha conjugate, we can do that because in the extremum of the likelihood function, the derivative with respect to alpha conjugate would be 0. So when we find the maximum of the likelihood, this gradient that we're calculating here, the derivative of j of theta with respect to alpha conjugate, would be 0. So we can use this equation. We take here the derivative of alpha conjugate, which means the first term, C tau Hadamard d Hermitian times x. The second term is not dependent on alpha conjugate, so it's 0. And the third term, when we take the derivative with respect to alpha conjugate, we get alpha times C Hadamard d Hermitian C Hadamard d, and we can equate that to 0. When we now further resolve for alpha, we get an estimate for alpha, and this is only dependent on x, c, d, nu, and tau in the end. And when we reformulate also the denominator, we can see that as if you remember that c Hermitian times c is equivalent to n, and d Hermitian times d is 1. That's why we get here in the denominator only n. And in the nominator, we have c Hadamard d Hermitian x. So what you can see is that the cross correlation between x and the model that we use divided by n provides us an estimate of alpha. Alpha is kind of an parameter, we could call it the complex amplitude, and this can be further decomposed into the square root of p times g of 0 times the phase, the carrier phase, the exponential function of the carrier phase. Yeah, now we have an estimate for alpha. We can now plug in alpha into our cost function, right? So we can do that. And by substituting alpha hat in the cost function, we arrive at this final problem. Very, very nice, because again, this is the absolute value square of the cross correlation of the received signal with our model parameterized by tau and nu. So we end up in a two-dimensional, this is a two-dimensional nonlinear optimization problem. And we can now try to solve that in general. Yeah? So there are many ways of solving this. For example, we can enter in a two-dimensional grid search. So what we do is we evaluate this cost function here at many values of tau and nu and look for the maximum. And say, okay, there's a maximum value. So the two values, or the two tau, the respective tau and nu that create this maximum value, they're our estimates. In general, the two-dimensional grid search is not really accurate because it depends on the resolution that you use for your grid search. You can then move to a gradient method or Newton's method with good initialization, because we are looking here in general at a nonlinear problem and we're looking at a non-convex problem. However, we will see later the problem is convex or concave in our case, because we're maximizing, is concave in a region. So around the global optimum, the problem is concave. So we could use an iterative method, but we have to initialize the estimate close to this, close to the global optimum. If we do that, then we can find also the global optimum by a gradient method. And in fact, this is how we are implementing how these two processes, acquisition and tracking, work. Yeah? Acquisition is the coarse initialization of our estimation problem, including a detection problem. We will see that. But in general, the estimates from acquisition are sufficient enough to initialize a gradient method. And we have seen the gradient method previously. This is the delay lock loop. We have derived that for the time delay estimation. So for the time delay estimation, we will initialize with the estimate from the acquisition, the delay lock loop, and it will start refining the estimates over time. And we will create something similar, which is a frequency lock loop or a phase lock loop. And we'll use the Doppler estimate to refine then with this phase lock loop or frequency lock loop the estimates over time, and track also the change of the parameters. So these two bullets that we have here, they are, the first one is perfectly representing acquisition, and the second one is then representing a gradient method, so the implementation in delay lock loop, frequency lock loop, and phase lock loop. And this we will discuss on tomorrow afternoon. Yeah, the signal phase phi plus minus pi, considering that g of 0 is -1 and 1, and power p can also be determined using the estimate of alpha, because yeah, the absolute valued square of alpha is equivalent to p, and the estimate of the phase plus minus pi, an ambiguity of pi, is the argument of alpha. Because why plus minus p? Because we don't know the data symbol. But in principle, we can also derive these estimates from these time estimates of time delay and nu. If they are precise enough, we can go back to the formula of estimating alpha and plug that in. We get a phi and a estimate with an ambiguity of pi and a power estimate. Yeah, grid search. So this, I told you already, we will use a grid search for the acquisition in general. And it's about how to do this grid search. But first, okay, the final cost function that needs to be evaluated for this grid search is also called the cross ambiguity function. When you are working in the field of radar, you will be very familiar with this term. This is used also in radar problems. And for the period k, we can write that cross ambiguity function here as the cross correlation x Hermitian k of c tau Hadamard d k of nu. We take the absolute valued square of that. Yeah, to select a suitable strategy to evaluate the CAF and thus to find its maximum, we have to inspect the shape of the CAF for the problem at hand. So this is very important. We need to understand how is our problem, the condition of our problem. Basic strategies in GNSS acquisition to evaluate the CAF are, so we can use, for example, serial search. So we use pairs of time delay and Doppler frequency values. They're called bins, these values, and we evaluate them one by one in a certain strategy, okay? Until we find a value that's above the certain threshold that we will use. Okay, good. We can also use parallel time delay acquisition. We take all possible time delays, are evaluated in parallel for each Doppler frequency bin. And then there's also parallel Doppler acquisition. So all possible Doppler frequencies are evaluated in parallel for each time delay bin. We will decide for the parallel time delay acquisition in this short introduction on acquisition, because it's we have a very nice implementation for this when we code this. Yeah. In a hardware, we have to decide what is really a good strategy. Yeah, so let's talk about the detection problem. We talked about now about the estimation problem. Let's talk about the detection problem, because we need to detect is the satellite signal present or not. And in the same time, we need to estimate the parameters of each satellite, whether it's present or not. So it's a joint problem. So the signal acquisition determines the presence or absence of a satellite. We have the two hypotheses. Hypothesis 1, the satellite is present. So we have the hypothesis there's then that X, our realization, is signal of a satellite plus noise. If the satellite is not present, hypothesis 0 means that X is just noise. The hypothesis 0, also called the null hypothesis, is fulfilled when the desired satellite signal is not received. H1, also called the alternative hypothesis, is fulfilled when the desired satellite signal is received. This type of detection problem is called the binary hypothesis test, because we have two hypotheses. Okay. So now we can look into detection theory, and we find for a binary hypothesis test, we easily find the Neyman-Pearson lemma to maximize the detection probability P of D for a given probability of false alarm. P of F, and that's equivalent to rho, decide the hypothesis H1 if. So we take here the what's called the likelihood ratio. So the likelihood for hypothesis 1 divided by the likelihood of hypothesis 0, and this should be larger than the threshold gamma. The probability of detection means that we can find whether the satellite is present, and the detection of the probability of false alarm means that we have falsely detected that the satellite is present. And we can calculate the two here. The probability of false alarm is the integral of X with the character, or with the property that the likelihood ratio X is larger than the threshold, over the likelihood dependent on the hypothesis 0. And this would be equivalent to rho. This is also how we can now define the threshold, because we can find that the integral, we have to scale gamma such that the integral is equivalent to the desired false alarm probability. Then the probability of detection is for all X, the integral over all X, with the property that the likelihood ratio test is above the threshold, over the likelihood with respect to the hypothesis 1. So this is Neyman-Pearson lemma. Yeah, now we can look into what does this really mean, the Neyman-Pearson lemma. Okay, we have the likelihood of the hypothesis 1, so the satellite's present, dependent on theta also, because we can see here the likelihood for this case, and then we have the other case that there's only noise is present, so the X has the distribution of the noise. Yeah, and the likelihood ratio can be given by this now. So when we plug in this here and we plug in this here into the LR, we get here the likelihood ratio as the exponential function as given here, and this should be larger than the threshold gamma, which can be derived from the desired probability of false alarm. And when we now apply the logarithm on both sides, we get here on the left-hand side the argument of the exponential function, on the right-hand side then the logarithm of the threshold. We can further expand this and rearrange this problem. For example, now we can multiply on both sides with sigma n square, and then we can also remove here from the second term. We can also see that the second term is Pn, because alpha times alpha conjugate is P, if you remember our definition of alpha. And remember that C tau Hadamard Schur D0 of nu Hermitian, I'm sorry, times C tau Hadamard Schur D0 nu, this is equivalent to N. So we have here minus P times N, and if we put plus P times N on both sides, we can reformulate this. We arrive at the second row, and now we can recall that a complex number plus the conjugate of a complex number is twice the real part of a complex number. We can apply this also for complex vectors. So on the left hand side we can then write twice the real part of alpha x Hermitian C tau Hadamard Schur D. And we can then divide on both sides by 2, and we arrive at the final problem that we need to evaluate now. So we need to evaluate the real part of alpha x Hermitian C tau D with respect to tau and nu, and this needs to be larger than this nu threshold. We can define gamma prime, which is equivalent to sigma n square logarithm of gamma plus Pn divided by 2. Yeah, in case the parameters, and this is the case the parameters are known. So in case the parameters are not known, we have to move to the generalized likelihood ratio test, which is called the GLRT. And then we combine the estimation with the detection problem now. In case the parameters theta are not known, we can define the detector to the decision to decide hypothesis 1 if. So we decide hypothesis 1 if the GLR, the generalized likelihood ratio, is larger than the threshold gamma, and while we plug in the estimate for theta as we don't have the true theta. So where theta is the maximum likelihood estimate of theta maximizes, or theta maximizes the likelihood. On an equivalent form is to decide H1 if. So we can now write the likelihood ratio maximized with respect to theta. This is what we have to solve the problem. Now we arrived at our combined detection and estimation problem. So now what we can do is we can now expand again the likelihood ratio inside this maximization problem. And we arrive with this. When we now move on and further expand this, we can plug in the likelihood ratio, and this is equivalent to sigma n square of log gamma. And now again, taking the derivative and so on, plugging that into our problem, we arrive at this final problem. So on the right hand side we have the threshold, which is gamma prime, and on the left hand side we have this maximization problem of the calf finally. So when we solve this, so we need to estimate tau and nu, and we need to also find estimates for tau and nu that are above the threshold. When this is given, hypothesis 1 is fulfilled, and we have estimates for tau and nu, initial estimates. If we are ending up below the threshold, then there is no tau and nu, so there is no satellite signal present, so we end up with hypothesis 0. So this is in principle how the signal acquisition works. And we can now move on to applying parallel time delay acquisition. So we in general, acquisition solves the generalized likelihood ratio test. We can also apply other statistics, other detection approaches. And now we will implement a parallel time delay acquisition. As I mentioned before, there's also the serial search or the parallel Doppler acquisition. We will not look into this in this lecture. We will apply the parallel time delay acquisition because it's a very simple implementation. At least for software implementation, it's very simple, and we can easily understand what's happening. Yeah, first of all, I'm repeating a little bit what's the discrete Fourier transform, because we will need that for our derivation of this parallel time delay acquisition. So the DFT, the discrete Fourier transform, we can define the analysis equation of a signal X here. And we can also use the operator DFT here. And the frequency part, the frequency representation is X of M here, and the synthesis equation is the inverse Fourier this is the inverse discrete Fourier transform of X of M here, and we arrive back at X of M. Now, in case if we apply, for example, a circular shift in case of a finite sequence X of n, a shift in time or in frequency only makes more sense as a circular shift. This is the difference to the continuous time Fourier transform. The circular shift properties can be given as, so we have the DFT of x n minus n modulo n, and this is equivalent to the exponential function of minus j2 pi m n 0 divided by n of x of m. And we can also write the inverse time shift. So the shift in frequency is then the DFT of the exponential function of j2 pi m0 n divided by n times x of n. And this is equivalent to x of m minus m0 modulo n. And the modulo operator can be defined as, and I have here just some explanation for that to remind you. So a modulo b means a minus b, and then a divided by b, while we take the maximum of a divided by b, that is an integer number. Yeah. So the smallest integer number closest to x. This is what we take here in this second term. And for example, we have then minus 4 modulo 5. So minus 4 minus 5, and this is minus 5 divided by 4, which is minus 0.8. And then we take the smallest number here, and this would be then minus 1. And then we have 4 plus 5 is 1. Yeah, in the second example, 4 modulo 2 is 4 minus 2. And yeah, it's so so, and then the next one is 4 minus 2. 4 divided by 2, so this is then 4 minus 2 times 2 is 0. It's just to remind you how the modulo operator works. Yeah, and then also cross-correlation can be given as two finite duration sequences x1 and x2 of duration n. So we have the DFT of x1 is x1 of m, and the DFT of x x2 of n is x2 of m, and the endpoint circular cross correlation then can be given as Cn, and this is the sum of p from 0 to n minus 1 of x1 conjugate p x2 and then p plus n modulo n, so that's the circular shift here, and n is between 0 and capital N. And the endpoint DFT of z of n can be given then by z of m, and this is the double sum, so the sum of n0 to n minus 1 and p of 0 to n minus 1 of x conjugate p x2 p plus n modulo n times e to the exponential function to minus j2 pi mn divided by n. So why do we need that? Because we can calculate this circular cross correlation. I'm expanding this here now. We can reformulate this by breaking up here. In the end, we are rewriting this exponential function, yeah, because we add here minus j2 pi mp divided by n, and we multiply again with e to the j2 pi mp divided by n. So we are not changing anything. This is just rewriting it. And then we can reorganize that because this guy here is only dependent on p and not on n. We have also here, this guy is also only dependent on p and not on n. So we can separate these two factors now. We have the sum of everything that's dependent on p, and then we have inside the sum of everything that is dependent on n. We can clearly see that here this is a circular shift now. So we can apply this from before. This would be then x2 of m e to the j2 pi p mp divided by n times e to the minus j2 pi mp divided by n. And we have also here then these two terms, x1 conjugate of p exponential function j to the exponential function of j to the pi mp divided by n. And now we can see that this is the Fourier transform of x. We have here, this becomes 1, the multiplication of the last two terms, and the first sum is the Fourier transform of x1 conjugate. So we arrive at that the Fourier transform, the DFT of the circular cross correlation function is equivalent to the conjugate DFT of x1 multiplied with the DFT of x2. And we get to a very nice implementation now of this, because we can use the DFT of x1 conjugate multiplied with the DFT of x2 and the inverse DFT, and we get to the cross correlation function in time. What have we achieved with this is that we can calculate the cross correlation function based on the time delays of our received signal and model signal. So we can calculate the cross correlation between the received signal and the model, but only in the resolution of the samples n. But this is coarse enough for us to find usually this maximum that is above the threshold to decide whether the satellite is present or not. We can reformulate also now this with matrices. So there's a matrix representation also of the DFT. So when we have an element of this matrix mn n, and this is the exponential function to minus j2 pi mn divided by n. And we can now write the DFT here of x using this factor, or this factor w here, and then also the IDFT, so the inverse DFT, and finally we can also write this in a vector form here using These elements of the matrix Wn are these WMN n elements, and we have XF is the frequency domain vector, and we have the time domain vector X, which is our signal then. Yeah, and there are some, and X is, yeah, it's the frequency defined vector, so a capital X0 to X minus N, Xn minus 1. We can also define by this the inverse Fourier transform, and the following interesting properties are given. So the inverse of Wn is 1 over n W conjugate. W times W conjugate is n times the identity of n, and W conjugate is equivalent to W Hermitian. And the DFT matrix is also called a van der Monde matrix, used in many applications for signal processing. Yeah, now we can reformulate our problem, and especially the vector-based signal model. We can now introduce here the DFT matrix, and we can use the DFT, so we can now exploit the formulation of the circular cross correlation using the DFT to perform a parallel time delay search for each Doppler bin. So we choose one Doppler value, and then we can evaluate with this cross correlation, circular cross correlation, all possible time delay estimates in the resolution of the samples of the signal. So we can write here that the CAF vector is Xi Hadamard Xi conjugate, and this vector Xi then is the inverse Fourier DFT matrix times, and we have here then the DFT of X conjugate, Hadamard with the DFT of the model that we choose. And the model is for time delay 0. And we can then put several Doppler bins. So we will change the Doppler here. And the output where the Doppler bins and the evaluated time delays are. So the evaluated time delays are automatically given by the vector Xi then. And the Doppler is for each, we have a vector Xi for each Doppler value that we can choose from this set here. Nu of from D of nu. Yeah, and then it goes from a chosen minimal Doppler shift to a maximum Doppler shift, and for each of these Doppler values, we will evaluate all the time delays from 0 TS, 2 TS, up to n TS. And the resolution of the Doppler is delta nu, and the resolution of the time delay is TS. Next slide, please. The complete CAF then can be given in a data matrix. So we can evaluate these vectors Xi, create the vector F as defined on the previous slide, and then create a matrix F, and then perform with the elements of the matrix F. We can look for the detection problem, which of these elements are larger than our defined threshold. Remember, the threshold can be defined based on the probability of false alarm that we select for our problem. Yeah, so for each PR sequence C of 0, a matrix F has to be derived. So for each sequence, for each satellite, we can get one of these matrices. In case a satellite was detected, so if one of the elements is larger than the threshold, using the GLRT, the maximum element of F is used to derive the initial estimates of Doppler and delay. And the resolution for the Doppler has to be chosen such that the following parameter tracking process can be initialized properly. This is something that is not really well explored so far, I think, but in general, the resolution of one chip is enough to initialize the delay lock loop. So if we have, for example, then 3-4 samples per chip, we have a good chance to initialize the DLL at least with an accuracy of one chip. In time delay estimation, error Doppler usually is about like 1 bin. Yeah, 500 to 600 hertz is a good value that we should be below to initialize the FLL or the PLL. And then the last slide, we can see an example of the cross ambiguity function. So we have here on the left-hand side the Doppler bins from 5,000 to minus 5,000 hertz. This is a reasonable range because of the relative motion of the satellite to a static user. We are not expecting a Doppler higher than 5,000. On the right-hand side, you can see on this right axis, you can see the time delay, and this is now here in, this is in samples, given in samples, because we have 4,000 samples, which means a 4 megahertz sampling rate. And we can see here that there's a peak strongly forming, which means that there is a satellite, and this relation of the peak to the noise is quite large. So we have also a good SNR. We can also observe that the problem is only concave around this global optimum, and if we move farther away, it's not concave anymore. So clearly, this is a two-dimensional nonlinear problem that we have to solve. But this resolution in time domain, so time domain is a resolution of samples, and here we have the Doppler resolution can be chosen usually manually here or chosen adequately. We can evaluate this cost function really nicely to end up on the we just need to end up on in this convex, in this concave region, and then we can hand over to the delay lock loop and phase lock loop and frequency lock loop, and we will talk about this tomorrow afternoon. So thank you very much for your attention. Are there questions in the room? Not yet. Do we have questions in the chat? No, yeah, it's already late. So thank you very much for your attention, and we will continue tomorrow for the online part at 9 Brazilian time, which is 2 o'clock, so 1400 hours, all right. So 2 o'clock in the afternoon, so Central European time. Thank you for your attention. We will later here continue with the second lab, looking at the code that I distributed on the drive. So yeah, have a nice evening in Europe, nice time wherever you are, and a nice coffee break here in Fortaleza. So see you tomorrow or later.